Thank you very much for the opportunity for this. But just very quickly, solar energy in Ireland has seen a checkered history. 4 years ago, we established this particular cluster to bring together those with interests in attempting to resolve certain problems. The cluster is funded largely by Science Foundation Ireland. Well, I'll correct that in a short while. In fact, we have significant other funding. But it's three institutions, UCD and DCU, Dublin City University, and ourselves, as well as the University of Limerick. And because solar energy, our solar companies in Ireland are relatively few and far between, but we have managed to actually encourage a number of those who exist to join us. SolarPrint is a small company that started a couple of years ago. Glantro is also very recent, only a year and a half old. Kingspan has been around quite a while. And these other companies, Mainstream Renewable Powers, evolved from Airtricity, which was recently purchased by SSE. And so these companies are now currently with us. The main philosophy behind our work is, as indicated, the starting date there was 2007, is to investigate and develop novel photovoltaic and photoelectrochemical cells and materials that can be used to harness energy, mimicking certain aspects of natural photosynthesis. So it's two major elements, and one can be considered short-term. Solar power is our short-term target in relation to PV technology, but focusing largely on third-generation PV. First generation is silicon cells, second generation thin film, and third generation is both a combination of these in different types, but also looking at particularly sensitized solar cells. And I'll come to a little detail on that in a minute. Solar fuels is another area of which, as a chemical engineer, I'm very keenly involved with this, because the storage of energy is a very difficult issue to overcome. And solar fuels is one way of doing it, storing the energy in the chemical bond, which gives a high energy density. And for example, production of hydrogen by water splitting is one aspect of this, or the reaction of hydrogen with CO2 in a recycled type of process like artificial photosynthesis to generate low molecular weight fuels and chemical feedstocks. This is the short term. Hydrogen, if you wish, is a medium term goal, and CO2 is a much longer term goal. But the rise in the fact that we are still going to be using fossil fuels throughout this century, and probably well into the next century, there's going to be the issue of associated CO2 emissions is always going to be with us, at least for a number of generations to come. So we're going to have to develop ways of capturing and also dealing with this problem in a rational way. The technology focus in photovoltaics, as I mentioned, is largely for the purposes of our research is in sensitized solar cells, which are operable in diffuse and or low light environments and indoor lighting situations. Those of you who may be familiar with photovoltaics, we're largely looking here at the Grätzel cell and or modifications of it using dyes, and this is a very simple mimic of the chlorophyll system in nature. Core capabilities that we have available to us, and this is in a sense, I'm appealing to those of you in the SME area who have interest in this, or who have technologies that are related, maybe not necessarily in solar, but have photonics or optical interests, that could be, if you see anything in this list or in any of the coming slides that you'd be interested in, I certainly welcome interaction with you. So deposition and screen printing technologies, we have expertise in organic dyes, are very important to improve the efficiency of these cells is one of the drawbacks. Currently the world record by Grätzel in EPFL is 13%. Device fabrication and nanotechnology, we are involved in this area. Aligned nanorod structures, this is because of the electron transport systems in these in these devices. It's very keen that you separate out the electron and hole generation systems that are created during the absorption of light. And so alignment and structure is a very important part of the design of these devices. Plasmonic enhancement, this is to actually trap as much light as possible, and modeling then the dyes and materials. Technology focus in relation to the second area is in the hydrogen production using photo-driven water splitting, and in addition to the either electrolysis or photocatalysis, photolysis, we are looking at what we do with the hydrogen once we have it. We've developed a catalyst that will assist in the storage of this particular material, but more importantly, for ultimate release. So we have currently the best in the world catalyst for hydrogen delivery. These systems up to 10 bar. Okay, we can deliver hydrogen at nearly equivalent conditions of gasoline engines. Also tandem cell development. This is the use of multiple elements of the solar spectrum for absorption purposes, and also in the reaction to reduce CO2 to components such as CO, which can then be taken further along, and methane and other compounds. Core capabilities, where we have metal oxide deposition techniques developed now, low-cost cell fabrication methods, and so on. And what we've achieved, I'll show you in a second, and please bear in mind this is over a period of 4 years. The current size of the actual team is myself, I'm directing it, and then we have 3 co-PIs, Edmund Magner at the University of Limerick, Han Voss in Dublin City University, and Professor John Sheridan in UCD. The total team is over 70. We have 18 PIs and FIs. These are academic staff, researchers, a manager, postdocs, collaborators, and about 32 PhDs and masters, and a research assistant. The research highlights: we have now developed 3 new routes to low temperature sintered TiO2 layers, which are ubiquitous in a variety of these systems. 2 dye classes have been investigated, and we're looking at quantum dot sensitizers, as well as other near-infrared and far-infrared absorption possibilities towards improving the Grätzel cell. Ordered arrays of nanorods. Again, I mentioned the importance of structure here, and that is throughout all of these systems. And then novel photoanodes for 2 material classes based on, this is water splitting, and in addition to this, we have we're developing molecular catalysis for oxygen evolution, which is one of the key steps in the production of hydrogen. Devices with low-cost photoelectric chemical cells. We're focusing on low-cost materials. There are very exotic materials out there that can actually generate this kind of hydrogen from water splitting at high efficiencies, but these are going to take a long time, if ever, to come into the commercial world. So we're looking at low-cost materials, nanocrystalline nickel oxide P-type electrode materials. This is for the reduction of CO2 using hydrogen, and heterogeneous photocatalysis using dyes that are functionally attached to this particular electrode to actually reduce the CO2. Modeling, a key element here is in modeling both classical and quantum simulations, looking at both the molecular atomic and the electronic states, in order to get a good idea of the band structures of these materials, because this is key to the actual design, and we're using this to actually assist in driving us towards the best materials possible. We have a lot of collaborations. These are all university, but like a lot more industrial collaborations, and some other collaborators down here. These are directly involved with us at this point, okay, across Europe and the US primarily. Some of our details you'll find, this website is on the UCD web generally, and you can contact us directly at these numbers here. I believe these are available, this set of slides. Yeah, so please consult if you wish. We have, these are some of our achievements over the last few years. We now have 6 industry partners. Nines PV is a very small company that just started up about a year ago in Ireland, is currently with us. These are our academic outputs. The 65 peer-reviewed publications is growing rapidly. For those of you in academia will say to yourself, over 4 years, this is relatively small, but please bear in mind that the PhD students are only graduating now, and a number of the academics involved here have slowed down the publication rate of this material because it's IP sensitive. We've delivered many presentations at conferences, and in addition we've achieved leverage funding over and above what we originally received from Science Foundation Ireland, which was 4.6 million. We have now an additional 7 million associated with a significant growth in our analytical capability in labs, in scanning electron microscopy, transmission electron microscopy, as well as a range of different other technologies. So we have a broad suite of capabilities here. So I would like to invite anybody from the SME community here, if you have an interest, certainly like to help. And I was discussing with one of you earlier this morning. I think we may be able to assist you. Okay. Thank you very much.